everybody, and good afternoon and good evening for those of you on different parts of the world. My name is Isaac Montoya, and I'm the Director of Marketing here at Uptime Technologies. I would like to welcome and thank you all for joining us for our 4th Annual Airflow Management Awareness Month. For those of you who may be tuning in for the first time, a few years ago, we declared June as Airflow Management Awareness Month with the intention to not only raise awareness around airflow management, but around cooling optimization and data center efficiency in data centers as a whole. One thing that we have come to find out is, well, a lot of the best practices or principles around cooling optimization, data center efficiency, and airflow management might be well talked about and in some respects, maybe even well known. They're not always well practiced. So one of the goals that we have here with a lot of things that we do at Uptime Technologies, but definitely with Airflow Management Awareness Month, is to help migrate the industry from not only common knowledge, but to common practice and actual application. So that's, kind of Airflow Management Awareness Month in a nutshell. And like I said, this is our 4th week, and actually our 4th and final week of this year's Airflow Management Awareness Month. And we are joined here today by Kevin Kent. He is the Data Center Operations Manager at the Ohio State Wexner Medical Center. We are glad to have him here, and he will be talking about data center energy consumption and how your data center can become energy efficient. We also have Lars Strong, Upsite Senior Engineer and Company Science Officer, joining us here on the call as well. So before I kick it off to Lars and Kevin, I just wanted to go over some quick housekeeping items. So this is the 4th and final week of Airflow Management Awareness Month 2019. And for those of you who may have missed our first webinars, we had some really good ones. In week 1, Lars Strong discussed liquid and air cooling and why a blended approach between the two is going to be the norm for the majority of data centers moving forward. In week 2, we were joined by Bill Clayman, the Executive Vice President of Digital Solutions at Switch, and he gave an encore presentation of his Data Center World keynote address on the State of the Data Center Industry Annual Report. And last week, we were joined by Aaron Wemhoff and Rahan Khalid of Villanova University, who presented a recent project of theirs on thermal control strategies for reliable and energy efficient data centers. So like I said, if you missed those, we will have those on demand for you to watch at your leisure. I'll share a link here later in this webinar for you to watch those if you missed out. So again, we are joined here today by Kevin Kent, Data Center Operations Manager for the Ohio State University Wexner Medical Center. Kevin Kent is also a board member for the Data Center Institute and a vice president for the Central Ohio AFCOM chapter. He has spoken at many different industry events around the world on data center energy consumption and data center efficiency. And he really has, the ultimate objective to reduce the overall data center industry carbon footprint. So a lot of what he talks about at a lot of different trade shows, and what he'll be talking about here today, is the different ways of how data centers can become energy efficient, and also why it's important for data centers to be energy efficient and reduce their carbon footprint. So before I kick it off to Kevin, we'll be joined here by Lars to say a few words.
Thank you very much, Isaac. And it's a real pleasure to have you with us today, Kevin. We've both spent a lot of time in the industry sharing best practices and the application of those best practices with end users and speaking at events. And I'm really looking forward to hearing you share this presentation with everyone today because you've spent a lot of time applying those best practices and that science behind the best practices to a number of facilities, and really looking forward to that practical revealing of the results that can occur. So thank you very much for being here, and look forward to hearing your presentation.
Okay, Lars, thank you very much. And Isaac, thank you as well. I've had the great pleasure to sit through many of Lars's presentations and the work that he does, and Isaac in his blogs, and the work that Upsite Technologies provides has helped me out tremendously, both in my own data center and some of the work I do outside of Ohio State. Is very much a privilege to be here today. And Lars and Isaac, thank you very much for the opportunity. And I'm going to request control here. All right. Sorry about that, guys. Okay, I have actually a whole bunch of information in here. I'm going to spend very little time on the first few slides. I know you guys all will have access to this, and these first few slides will tell you a little bit about myself, places that I have presented, and places that I'll be presenting in the upcoming future. So part of traveling around the world, I've had the opportunity to meet a whole bunch of global data center leaders. There's no way for me to fit all of them on here. I put these pictures on here because each one of these people have a little bit in this presentation. A few that I would like to point out here in the middle with the plaid shirt and the glasses, that's Professor Ian Bitterland he's from the United Kingdom. He is one of the authoritative forces on data center energy consumption, number of connected devices, and I've used his research data quite a bit. To the right of him in the middle, where the picture of me not having a beard, that's Mike Andrea. He's from Sydney, Australia. Mike is actually a brilliant man. He is sitting on, I don't know if they call it the president in Australia, but he's working with the Australian government to try and figure out how they can rein in energy consumption in Australia, and continue to learn a great deal from him as well. I work with several environmental foundations. I listed them on here. If you're interested in looking at any of them, feel free to do so. Each one of them sort of has their own niche and unique way they're trying to assist our environment and to help our planet get a little bit healthier. Okay, so the agenda, we're going to go through PUE, Power Usage Effectiveness, Level 1, 2, and 3. We're going to talk a little bit about ASHRAE and the standards and how those can benefit us when we understand them and apply them. We'll talk about how you can measure and calculate your own data center carbon footprint, and just a whole bunch of other airflow management items that I have put in this presentation. When we get through the first bit of this and towards the middle and the end, I have 3 live data center scenarios where we applied basic principles and we're able to make significant changes, or are making significant changes, and things that would apply to your data center as well. I mentioned Professor Bitterland. Much of the data that you see on this slide comes from his research. And as I said, he's one of the authoritative sources for this. But the reason we look at data center energy consumption, one is very expensive for power and cooling to run a data center. The end user demand, the need to always be connected wherever we are. When I travel abroad, I have to have a SIM card that allows me to connect when I'm not on Wi-Fi. I need to be able to talk with my kids, check bank account information, LinkedIn, all of those things. And another big item that's really driving the growth of data centers and power consumption is autonomous vehicles. And that is going to continue to grow along with the Internet of Things and the technology that is there. What we're trying to figure out how to do in our global data center community is how can we have this technology and not harm or cause further damage to our planet? And the best way that I know, and the best way that I've heard Lars and Upsite talk about, is understanding what you have and being able to maximize the efficiency without, and this is the most important thing, without affecting the reliability and the overall health of your data center. One of the figures I like to talk about is 416, almost 420 terawatt hours of electricity. Our best guess is 65% of that is being produced by burning fossil fuels. There is great work being done with renewables. We see our larger hyperscale facilities, Apple, Google, Amazon, they are using a huge, if not all, portion of renewable energies. That is a very small number of the remaining 8 million data centers globally, and trying to figure out, again, how to use the energy that goes into that facility as effectively as possible is going to help both in your cost savings and also in the amount of power or electricity that we're consuming. Right now, the IT industry, it is between the 2 and 5% of all carbon emissions. And by 2040, we're going to be guessing in the 14% range or higher. But I think one of the most important things to understand about this is all of the research, the innovation, the new technologies that come through data centers, I believe will provide a footprint for much of the business industry to follow. So when we can get this figured out, others will follow, and it'll have a significant positive impact on how we use energy, the type of energy we use, and then having a better or a smaller impact on our planet. And when we look at why energy efficient data centers matter, this slide is very telling. It came from the Green Data Centers publication. When we look at the basic things, the airflow management, consolidation of servers, the improving processor and technology, we see this. The hyperscale facilities are excellent at this. And one that is very, very important to me is the last one, where it talks about set points and raising temperatures can be a 60% reduction in cost. Where we look at all of these things, what they can add up to in the equivalence, it is very significant. And I think you'll see as we go through this presentation and start looking at some of the live scenarios, very small little basic changes can have absolutely huge effects and outcomes in the positive nature for your data center. Okay, power usage effectiveness. This is probably, other than climate change, one of the most hotly debated topics as I travel around. It seems here in the US we're a little more accepting of it. I know in Australia they came up with their own parameter called neighbors. It is very similar to PUE, and I'm certainly not an expert, but generalizing, if Tim, if you join this call maybe towards the end, if I speak incorrectly, you can help me with this. But basically what neighbors will do in their measurement is they will take the outside humidity and temperature into the factor of PUE. But case in point, if I have a 1 megawatt facility in Miami, Florida, and it has a PUE of 1.5, and I have absolutely identical everything of an identical data center in Wyoming, and it's at a 1.5. Well, I could argue very much that the facility in Miami dealing with the high heat and humidity compared to the Wyoming no humidity, lower temperatures, I would argue that the data center in Miami is far more efficient or effective in how they use their power. The reason that we use PUE is this: you cannot manage what you do not measure. PUE provides us a baseline to which we can measure against, but most importantly, it points us in the direction of where we're not using our power effectively, and it allows us to focus in on that and make the changes needed so we can be using the power effectively. This slide comes straight from the green grid, and actually the next few slides will, explaining how PUE is calculated. And it is very simple. It is your total facility power divided by your IT equipment power. And as we go to the next slide, we take a look at what is considered very efficient and what is considered very inefficient. And I think this has changed a little bit over the years. During the Obama administration, they came out and said, we want all of our federal data centers that are existing to be at a 1.5 PUE by 2020, I believe was their end date. And all new federal data centers opening up needed to be at a PUE of 1.3. I think that when we look at efficiencies and trying to make effective use of the power coming into our facilities, that the 1.3 to 1.5 is more of the range we look at, where a few years ago we're like, hey, if you're at 2, then that's pretty good. And I think a lot of data centers were trying to hang around the 2 for PUE, but certainly the 1.3 to 1.5 seems to be more of the industry standard. So if we go to calculate PUE, having a PUE as close to 1 as possible is the goal. I don't know that is right now with the technology we have completely possible, but the idea says if I have 2 watts of power coming in, 1 watt for facility, 1 watt for IT equipment would be our ratio. And here's another example that shows us what a PUE of 2.0 would look like. And again, that was that's still not a bad PUE, but the technologies, things that techniques that Upsite has used and teaches when they are at trade shows, and deploying those techniques allow us to get to PUEs a little bit lower than 2.0. Okay, so there are 3 levels of measurement with PUE. PUE level 1, 2, and 3. I want to talk about all of these very quickly, and then I'll show you how they can be used in a live data center. So if we go to PUE level 1, this is a basic measurement, and it's measured at the output of the UPS system. The picture I have up here, this is from a very old UPS system. It's a 9315, but we have an I/O board on there that's pretty standard, and most UPS systems, and I have not seen one where it does not have an I/O board where you can read the output. And that's where we would start to get our baseline measurement information for a PUE level 1 reading. When we go to PUE level 2, we are now going to look at the measurements of what I would call the floor PDUs within the data center. And again, this is a picture of a very old, what I would consider outdated PDU. But again, we have the ability across the phases to see what the load is. And that is how and where we would get our measurements for PUE level 2. One of the things that I do on a weekly basis when I'm measuring PUE is I will actually go to the floor PDUs. I know the makeup of our floor PDUs. I know which UPS system they're tied to, and I try and do a check and balance to say, okay, this is what I'm reading here. Is it matching or fairly close on the UPS? It might not always be exact because of the power factor associated with the UPS system, but should be really close in what I'm seeing from the floor PDU to the UPS system. Finally, PUE level 3, this is what we would consider, or the green grid would consider advanced. I see a lot of DSIM solutions now that have PUE modules in them where it's measuring the PUE real time and as you go. When we look at PUE level 3, the IT load is measured back to the power distribution units or the power strips within the rack. I've taken a picture of what one in a newer rack in our data center looks like, and also through our DSIM solution, we are able to see what our load is there. And again, the PUE level 3 is basically real time where it is constantly measuring that load, and it allows you a minute by minute to see where you are. So I know when I first started looking at PUE and the measurements of PUE, why does it matter to me, you know, minute to minute, 5-minute segments, 10-minute segments? Even from the PUE level 1 measurement to if you were using PUE level 2, you could see a little variance in what your PUE is just based on the measurements, the power factors that are associated with the UPS system. But also this, as your CPU utilization ramps up and down based on the number of users or traffic that you have in your data center, that's going to affect it. And also your outside temperature, outside humidity will have a great effect on there also. And it's really important as we understand and can get a little more granular and how those outside variables affect our PUE. It goes back to if we're measuring this and we're understanding if it's 95 degrees in Ohio and humid, I know what my mechanical equipment is going to do. I know what during my peak load, what my CPU is going to do. And it allows me to make provisions to not only maintain my efficiency, but to make sure that I'm doing absolutely nothing to harm the reliability and health of the equipment and the facility itself. Okay, this is straight from the green grid. It pretty much summarizes what we just talked about, the level 1, level 2, and level 3 PUE measurements. It tells you where the IT equipment energy is measured from, the UPS, the PDUs, and then the actual rack PDU strips themselves. Also talks about the measurement intervals, monthly, daily, every 15 minutes. The recommendation that I would make to anybody listening, I was so overwhelmed by the idea of PUE at first. I'm in a mixed facility. It took me 18 months to find an electric bill, and it was incredibly difficult to try and start slicing and dicing the things out that I didn't need and focusing on what we did need. But it really became very simple when I started to understand better the level 1, 2, and 3, and it allowed me to focus in. I started with level 1, and I became very consistent. I know it said weekly. I did Monday, Wednesday, Friday, where I would manually walk around and measure. But here's the important thing. I was so concerned that I would do my PUE measurement wrong. And really, the only way you can do a PUE measurement wrong is if you cheat the numbers. If you see your facility, total facility energy, or your total IT equipment energy, and you fudge the numbers so your PUE looks better, that's the only way you can do it wrong. But if you are recording and following the exact outputs and energy usage that you see both on your IT and your facility equipment, you're not going to be wrong. You will learn how you can improve. You will learn how to get better from level 1 to level 2 and possibly even to level 3. And then you'll learn how to take that data to use it to your advantage to make sure you have great reliability, proper cooling, no overcooling, and you're managing everything within the data center as effectively and as efficiently as possible. So going through this so quickly, I wanted to put this slide in here. So we talk about IT equipment, and then we talk about the facility equipment. And I think the way I can simplify it is anything that's in your data center and anything that's supporting, such as your fire suppression and detection, any DSIM solutions, any monitoring that you have, that is part of the IT equipment. When we look at the facility side, and this is where it can get difficult in a mixed facility, we're looking at HVAC, security, the whole building, power to the entire building itself for the facility which in the data center resides. So again, I was confused trying to decide what went where, but consistency is the key. If I, by some chance, counted some equipment that should have been part of IT equipment in with the facility, but if I did that measurement exactly the same every time I measured, I at least have consistency. And then later, as I would find out, you know, this probably should have been with IT equipment and not facility, it's okay to make that correction, but just be consistent with what and how you're measuring for PUE to be the most effective for you and how you manage your facility. This is the final that I'll talk about with PUE. I apologize. I've actually done this in a 4-hour workshop before, but I know I'm going quickly. But you will have these slides and can review them. If you want to connect with me on LinkedIn, that's the best way to get a hold of me. And any questions or any conversations you want to have after this, we can definitely do that. But this is just a great schematic drawing that shows us where our level 1, our level 2, and our level 3 would be. Again, we're looking at the UPS here as the level 1. We can go up here and see all the areas that are marked as our level 2, and in the data centers that the data center I manage and those that I work in, we see those going out to the floor PDUs, and then finally level 3, the actual power strips that we see within the racks themselves. And again, level 1, level 2, and level 3. Is any one better than the other? I mean, level 3 gives you the most granularity and the most real time with what is going on. But again, whatever level that you feel you can accurately measure and you're comfortable with, to start doing this and doing it at the regular intervals recommended by the green grid, you will not be wrong, and it will not be something that will hurt you in your attempts to gain efficiency in your data center. Okay, the ASHRAE Guidelines, the American Society of Heating, Refrigeration, and Air Conditioning Engineers. I used to joke all the time, this was a group that I wanted to hang out with and party on a Friday night. Of course, that was sarcasm, because as I read through their the ASHRAE Guidelines and all the updates and stuff they make, it's, to me, is dry, and some of it's above my level of intelligence. But as irony would have this, I'm now a paying member of the ASHRAE Society. And they provide something that is incredibly valuable to data center operators, data center owners, and anyone who works in facilities that has work within a data center. Mark Monroe, I had him, sorry I didn't mention him, his picture was on one of those first slides where I had the global data center leaders. Mark is absolutely a kind and brilliant man. He has been a independent consultant for years. Most recently, he was hired by Microsoft to develop their next generation of efficient data centers. This past fall of 2018, I was in Seattle with AFCOM Leaders Lab. We did a white paper on green data centers, energy efficiency, and Mark was our Leaders Lab leader for that. And having the opportunity to pick his brain and work with him was incredibly valuable. But he spent a lot of time on ASHRAE, and I want to spend maybe a little more time on this than I did on PUE. But I always very much focused in on the recommended guidelines from ASHRAE, which tell me where we see the A1, 2, 3, and 4, that's the class of server and equipment. There's actually a website. I want to say it's everyserver.org, but there is a website that can help you discern what class your equipment is. But let's make this safe assumption. Let's say that everybody has class A1 equipment in their data center. When we look at ASHRAE's recommended range, and what this means is, hey, for the best overall reliability of your equipment, your lowest failure rate due to your environmentals, this is the range we recommend. And they say no lower than 59 degrees and no higher than 89.6 degrees. When we measure temperatures within the data center at the rack level, ASHRAE recommends that we have bare minimum the end of each row. We have temperature sensors at the bottom of the rack, the middle of the rack, and the top of the rack. And additionally, as a minimum, one rack in the middle of that row to completely fill that out. And if you look at that range, it's fairly wide. And as I was in my own data center and go into several others, I don't always see temperatures at the 59, but I'll see temperatures in the 66 to no more than 70 range. And as we look at this on a class A1 server, they're saying you can go up to at least 90 degrees on A1 equipment and still have the least amount of risk of failure to your equipment. But as we expand into class A2, A3, and A4 servers, you can see the huge temperature ranges that they show us here. So again, the recommended range was very small, and then they go to an allowable range that tells us, hey, we realize that the server, switch, and storage manufacturers, that their equipment is becoming more dense, that they are doing everything in their design capabilities to make servers more efficient and not have such a deep need for extra amounts of cooling. So if there's one thing that you would take away from this session today, this is one of the slides that will help you the most, is understanding those guidelines, how to live within them without affecting reliability, and staying within them to get the greatest amount of efficiencies in your data center. And this, to me, was a funny slide. Mark had this in our Leaders Lab workbook. We're not suggesting that you keep your data center at 95, but what we're suggesting is this, is that you understand the ASHRAE recommended and then the allowable envelope, and that you learn proper techniques to safely increase those temperatures where your equipment and your mechanical equipment and your IT equipment are operating at a very efficient level. And I will show you, I believe here, yes. So David Moss from Dell, he came up with this very simple but incredibly accurate way to find what we call your sweet spot. And that is, we want to have our set point and the amount of cooling we're provided. We don't want to give the equipment not one drop more than what it needs. So David Moss came up with this technique. I use this all the time. And in every data center that I've used this, set points between 76 and 82. Over the course of 48 months, I've not had one equipment failure. And the reason is I followed ASHRAE guidelines, I measured PUE, And I use this simple method from David Moss. So the idea is this: you want to have a measurement for your PUE. And I would recommend, if you do this, that you're doing it on a very hot middle of the afternoon day when the load is heavy. Why? If you can get it to function and survive properly in the hottest, heaviest moments of your day, then you know you will be good throughout the 24-hour time period. But you'll measure your PUE, and you would start to raise your set points 1 degree at a time. To be honest with you, I'm impatient, and I have found that for me that it seems like it takes about 2 degrees to affect compressor cycle change. But 1 degree is good, and what happens is you raise that set point 1 degree, you allow the system to stabilize. I do a lot of this: walk up and down the rows that crack unit is supplying air to. I try and get a good listen to the CPUs. Are they ramping up? Are they staying the same? I do a lot of measuring of temperatures with an IR gun and temperature strips. And I just make sure that that 1 degree didn't cause any issues, or that it's not stressing or causing reliability issues with the equipment. And you continue this process. And I'm sorry, I left out an important point. After every degree, you want to measure your PUE again. You want to see where you're at, and is that ratio changing? And you continue through this process until you receive a PUE measurement that's higher than where you started. Once you see that, then you can back it down a degree or 2, and that's where David Moss says you will find your sweet spot. Why is this important? This next bullet point is what got me so interested in trying to gain efficiencies in Ohio State's data center and helping others to do so. It says every degree you raise your set point, you will lower your air conditioning bill 3 to 7%. I found that to be not true. It was my opinion. I didn't have any data or any science to back that up. And that specific sentence got me interested in trying to prove that wrong in Ohio State's data center. And as every day, week, month, and year went by, all I did was provide data to prove that to be correct. So if you are measuring your PUE, if you know the amount of kilowatt hours you're using for IT equipment and also for your mechanical equipment, you can start to quantify and see how a 3 to 7% savings over the course of a week, a month, a year would add up and be very, very significant. So again, this is a great technique. It doesn't require any special skills other than being able to measure your PUE and exercise a good dose of patience. Okay, I think I've mentioned some of these. Some of the basic measuring tools that I just purchased on my own, some of them Ohio State has. The temperature strips, I bought these. I saw these at a conference in Washington, D.C., and Lars did the 4 Delta T's, and I was really excited through the first 2, and then he got to the second 2, and I started to get overwhelmed, but he did a great job in explaining that, and it was very beneficial. But I saw these temperature strips there. I have several hundred of them. They're awesome. I have the ones that are on magnets. I'll put them top, middle, bottom, where we're having, where I feel like our airflow management issues, where maybe my stratification, the height to which the supply air is traveling in the rack doesn't look good. And I'll put them there and let them sit for a while and just get a good idea of what's happening. Also, when I have those strips up, I have a little bit or a lot of OCD with this. I'll take the IR thermometer. I'll go by and just hit where I have the strip, and I can tell you from my IR gun to the temperature strips, there's never a variance of more than 2.2 to 0.4 degrees. So it gives me a good comfort level with the temperature strips. The bottom one, the FLIR thermal imaging camera. This is, I have an iPhone 10. You can get them for Androids. I want to say this was around $200 to $300. Absolutely amazing video and pictures that you can get with these. And here's what's important. Sometimes it's difficult to see and know exactly where the air is going. I've done a lot of work with computational fluid dynamics modeling. Once you have a model built, it's not too bad to use, but it's pretty time consuming. And it's only as accurate as the data that you build into the model. But the FLIR is sort of a shortcut for me. I still use the CFD analysis for any changes, new things that we have coming in. But when I'm concerned about troubles, or do I have my ceiling tiles for exhaust air in the right place, This gives me a great visual, both picture and video-wise, of how the air is moving. I actually have some samples in here for you. And for the amount of money that I paid for that, it was very inexpensive and worth every penny. Now, this is where, if we're live, that I would have examples to hold up and show you. These basic airflow management tools are vital. I talked a little bit with Lars and Isaac and Alex about this yesterday. It's amazing. This is where you have to start with your data center. We have to look at closing up all the gaps, holes, empty rows, empty racks, and the items that you would need to do this are very inexpensive, but also will save you a great deal of money. So we look at the raised grommets, the area where your cables come in and out of the floor, so no air is leaking through there, as well as the foam air blocks. I already mentioned blanking panels. Normally, most racks have 42U, some 48, maybe a few more or less. We do not want to allow supply air to come from the front to mix into the back with the return air and vice versa. We want to do everything possible to separate our supply and return air so we have maximum efficiency with both our supply and return. The alternative materials, I believe I have some pictures. Ohio State, it's not that they don't have money, because they do, but we're very careful how we spend it, completely different from the public sector or a colo. And we had some rows that had empty spaces where we removed racks. We really didn't have racks to put in. They were really nice magnetic expandable panels. They were expensive. I was going through someone else's data center in Columbus, and I saw an alternative material that they had. It was somewhat like a corrugated, wax-covered type of cardboard. Very inexpensive. It was a packing material. I bought several sheets. It allowed me for about $80 to cover up some serious holes and blocks to show that, yes, this will make a difference. And then once I was able to show that, being able to get something a little bit nicer was easier to do. Floor tiles, very important. There are floor tiles that have been out for quite a while now, but I like to call them high def, or they're designed in a way where they supply much more air to the rack, and the stratification that these type of floor tiles gives is much greater than a standard perforated tile. And then, of course, the aisle indoors. Anything that we can do, again, to aid in the separation of the supply and the return air, that is the most important things we can do to help us with the efficiency in a data center. Okay, so why do we talk about cooling and everything that goes along with this? This was from the Uptime Institute. They produced the publication earlier in the year. This is great information. They said PUE, average global PUE in 2018 was 1.58, and for 2019, looking at it being slightly lower and a target of 1.35. Again, we have a recap of the kilowatt hours that have been used, but I love how they broke it down and said 150 will be used for something other than IT equipment. Most of that, other than IT equipment, gets broken down into cooling. And one of the most telling things, and I think this is at the bottom bullet point, it says in U.S. data centers, nearly $1 billion for 12.5 billion kilowatt hours of what they considered wasted energy. Average rate per kilowatt in the U.S. is around 8 cents, which equals about 110,000 tons of carbon emission. I have spent a lot of time trying to understand why in my own data center, why in other data centers that I go into, not just here in the US, but globally, where overcooling seems to be a real problem, and Uptime in their publication captured that very, very well. Okay, I don't know that this is something I completely take credit for. This is a chart I've used for quite a long time, and as I travel, people find this incredibly valuable. This is not precise exactly, but it is pretty darn close and more of a guideline for you to use when you're trying to size the cooling needs within your data center. And I break it down starting by tons, 1 ton all the way up to 30. And we know that 1 ton will travel roughly 480 cubic feet per minute, a throw rate, which means how far will that air travel and maintain the proper static pressure to allow the proper stratification of 2.4 feet. And most important, and the one I look at the most, I know 1 ton of cooling will mitigate 3.5 kilowatts of heat or power in a data center. So we go all the way back to the very beginning about measuring our PUE, knowing what our kilowatt load is. This is one of the reasons where I can't manage and size my cooling properly if I don't know the load I have in the data center. Again, this is a great chart. I used it in many, many places. And then I want to show you a practical application. Here's an example of 6 data halls. Here, that I love to do the rundown. 125 kilowatts for an IT load in hall 0. So if I were to divide that by 3.5, why? 1 ton of cooling will mitigate 3.5 kilowatts of heat. I see their requirement for kilowatts in tons is around 36. I saw in that room their actual cooling in tons was 148, and it came up to an extra 112 tons of cooling. Now, this becomes an important point. We always, in data centers, we plan for failure. We have redundancy in N+1, 2, 3, and 4 in almost every fashion that you can imagine. So newer technologies, being able to do what I call team crack units, where we connect the crack units through a network, a standard network switch where they all talk together and work as one. Now we can look at N+1 a little bit differently. And I cannot tell you what is right and what is best. Every data center has to make their own decision on this. But at Ohio State, our N+1 now is we have 2 20-ton crack units in standby. We have tested this over and over and over again. If one crack unit dies, it can call for the other crack unit to come up, or the other crack unit will see it. So they stay in standby mode and will come up as needed. I've seen some data center folks that have 24/7 staff where they can very quickly walk in and flip one on. I can't tell you what is best for you, but what I can tell you is here's a great way to size your cooling needs based on kilowatts. And then if we look down at the chart below that, we're also going to look at cubic feet. I'm going to use hall 0 again as an example. It had 3,204 square feet, 27,216 cubic feet. The capacity where they're cooling in cubic feet was 71,040 cubic feet. And again, we see an excess here. Why is this important? We're going to look at some of these data centers and we'll see that we don't just put all our equipment in one area of the data center, that it's spread out. The crack units, we do have to take into consideration not only the supply air, but if we have any type of plenum or any return for the hot air to go back, we have to consider the cubic feet distance and volume associated with that as well, so we can move both the supply air and the return air effectively. So again, these 2 charts will give you a great idea on how to size by kilowatt and also by cubic feet. All right, here we go, real life data center scenario. I wanted to put all of the information up here that I could think of. I think some companies would say, hey, we went in and did a power and cooling audit, and these are the basic information. This is the basic information we came up with. So you can take a look through here. See, this is a fairly decent sized enterprise data center. Certainly not a hyperscale, but basically 5,200 square feet. I went ahead and showed the cubic feet there. Some of the important things I want to look at is the IT load and the facility load. We'll show you why those are important here in another slide or two. I know they had 730-ton DX crack units. Supply air was coming out at 54 degrees. Their set point was 71, and their return air was 71. I'll go back to Lars and his 4 delta T's. If we look at the delta T from the front of the rack to the back of the rack, there is not really a delta T to mention. This is extremely important. DX units, they were designed to take as hot of air as possible, and the hotter that air, return air is, the more effectively it can compress and turn it into chilled air to supply the air for the racks. I did throw some other information down here. Average rack inlet temperatures, 60, 62, and 67. If we look at the ASHRAE recommended range, that's 60 degree. That's 1 degree above the bottom of that range. And I've never seen this, but I think about this all the time. If I have some pretty hot pieces of equipment, exhausting air in the 80 to 90 degree range, and I'm putting air in at 59. My worry at that bottom range, and I've not seen this happen, but would be the formation of condensation just based on the extreme cool air and the extreme hot air. And again, I've not seen that happen, but when I see a temperature at that bottom range, that's the concern that I have. Okay, when we look at a big portion of this, and I'm focusing specifically on cooling, this is airflow management. I immediately looked up to A16, and I noticed that there really isn't a whole lot of equipment there. And in enterprise data centers in the Columbus area, in the Sydney, Australia area, in the Madrid, Spain area, and many other places I've been, data centers that have been around a while, they shrink. The actual footprint is shrinking. And when these data centers were built, at some point they were at full capacity and required this cooling. But this is a great map that gives me an idea of what is or is not happening, how the cooling units are set up, and I want to show you some of the things that we learned from there. Most importantly, this is a PUA calculation. There's one that I use online, not because I'm not good at math, but because this calculator will give me the actual carbon footprint. When I calculate the load for this data center, I can see my PUE isn't great. It would be in the inefficient category. I can also see the amount that I'm paying for my annual power cost, and that the carbon footprint is nearly 3,500 tons. All right, as we start to assess this facility, we want to keep this chart in mind as we're looking, again, both at the cubic feet per minute that we need to supply, and also at the IT kilowatt load and what's required from there. We're going to start with the very basics. We're going to get our cooling calculation in kilowatts and cubic feet. We're going to see where the set points are, return temperatures, rack inlet, the rack exhaust. We're going to look at the room dimensions. Is there a plenum? We're going to look at floor tile cutouts. I love to do this. You're going to be surprised when you see what I do with the floor tile cutouts. We're going to inspect the perforated grills, the ceiling tiles. We're going to do everything we can to get a very good, accurate measurement of where the power is going in this data center, and are we using it effectively, and if not, why are we not? This is a screenshot from a DSIM solution that measures the electricity at the rack PDU level, and I just put that in there to give you an eyeball of what it looks like. Those are the raised floor grommets we talked about, some foam blocks, and this is sort of an after the fact. That's the alternative material to close up gaps in between incomplete rows. There's a better picture of it. Yes, and when we look at the perforated floor tiles, this is really common. The lighter gray tiles, those are what I would call a high depth. And here's what happens. I see this all the time. We get in a data center, we feel that these racks are a little bit too warm, so we must not be getting enough air. Let's throw another row of floor tiles in. When we do this, we are essentially decreasing the static pressure and essentially decreasing the stratification. We no longer can get the supply air up as high as we need to, and we start this self-ruminating cycle where everything gets entirely too hot. So here is what the cooling capacity would look like. Again, we've talked about that both in cubic feet and in kilowatts, and gives us an idea down here of PUE and what we're paying. Here's some thermal imaging that backs up a little bit of what I was saying about the floor tiles and how effective the thermal imaging can be. On the right-hand side, we see a very deep blue cloud in the return area. It helps explain the 71-degree return temperatures. Again, just some more thermal imaging that shows us exactly what's happening in the data center. And anytime we see the really dark blue, especially in areas where we don't have equipment, I would call that overcooling or not effectively using the cooling for the data center. Let me back up one more. Okay, this is just a great visual of recirculation of the hot air mixing with the cool air, how it should work, what happens when it doesn't work well, and why we work so hard to cover every hole, every gap, doors on the end of the rows, everything we can do to separate the supply air and the return air. So this was the actions that were recommended for this data center, and I think I mentioned all of them. We want to fill that all MTUs. We want to cover just every opening we can find. We want no air leaking out of anywhere that we don't have equipment that needs cooled. We're going to look at the set points, a crack unit cycle schedule. And I thought the eliminating zombie servers and equipment was going away, and it seems like it's reared its ugly head again. Okay, here's a breakdown of what we did in this data center. So we want to understand cubic feet. We want to understand that a 30-ton crack unit can cool 14,400 cubic feet per minute without losing static pressure and stratification. We also want to understand the distance that we have from one crack unit to another. I don't think I included pictures on here. AC20, AC18 fought each other. They would kind of meet in the middle, push the air away from where the equipment needed to go. When I look at the cubic feet per minute and the throw rate for AC20, AC20 can actually very adequately cool that entire area. And same thing, as we move through this data center, we start to realize that if we can go every other crack unit, we are going to be able to supply a little bit more of supply air than they need. But then the big one down here, this is no fault of the data center operators here. Just very quickly, the data center footprint shrinks. At one point, that area was full. This one was easy. That crack unit was not cooling anything, and to cycle that off became very easy. And what this data center is doing is they alternate every 30 days, AC20's on, AC18's off, and vice versa. So that gives you a really good idea. That didn't cost really any money to do that. That is using the math and science behind airflow management to see how can we more effectively use the cooling within our data center. Here's what this looks like. Here's where we started out at the top. This is the reduction so far that they've been able to make. Is actually going to be more. But what I really want you to focus on, little to no capital expenditure, understanding the math and science behind the airflow management, using that to your advantage. For that one room only, cost savings annually of over $300,000 and a reduction in the carbon footprint almost cut in half. Okay, I know we're running short on time, and what I want to do, this is more of the same. I wanted you to see an example of this floor plan. The thermal imaging camera really helped me discern how these crack units were fighting against one another, and another example of what Uptime showed as overcooling. Okay, Isaac or Lars, I want to turn this back over to you, so if there's any questions or answers we can get through and get everybody off here on time.
All right, thanks, Kevin. So we do have a few questions coming in. So the first one is by Mauricio. To measure PUE, what does it mean to measure the UPS input and output? The difference between input and output is added or reduced to the total facility energy. I think that's a question about the equation of calculating PUE.
Okay, so if we're saying why are we using and the purpose of pulling from the UPS area. So in my data center in Ohio State, all of the IT equipment runs through the UPS system. UPS or a level 1, that will allow me to see the load that is going in there, and then the output. This is what this UPS system would have to put out or supply to make that equipment run. And the reason for using that is just that, to discern what the load is on my IT equipment.
Okay, perfect. So the next question we have is by Eric Swanson. Allowable range is great, though I believe it's specifically for periods of time, basically saying not 100% at 89 degrees Fahrenheit, for instance.
Yeah, that's actually a really good point. And again, whenever I adjust set points, I always try and do it at the hottest portion of the day. I'm going to pick a really hot and humid day if I can, and also when I know the load is high. So the point that I think Eric is making, and it's a really good one, is, hey, let's not just drive the temperature and the set points up to 90 degrees and walk away and think it's great. We want to look at using that Finding Your Sweet Spot from David Moss, and kind of combining those two together. Understanding, yes, this is the allowable range, and I think what he said is very accurate. I don't think it's intended to say 90 degrees and walk away, but understand you have some room in there, and if you can just get 2 to 4 degrees increase, and use the sweet spot technique to make sure you're not overtaxing and bottoming out your equipment, you're going to do really, really well for reliability, and also feel very comfortable in the savings you'll realize back in your facility load and your kilowatt hours.
All right, great answer. We have another one from earlier in the presentation that asks, can PUE fluctuate throughout the day?
Yes, very, very good question, and I'm glad that person brought that up. So the PUE level 3, where it says, hey, it should be every 15 minutes, there are so many factors that can affect PUE, and the ones that are most common that I've mentioned are outside temperature and humidity. Obviously, through the evening and in the early morning hours, it's going to be cooler and potentially a little bit drier, and then also the CPU utilization and the load going through your data center. I have seen, not personally, but I have read reports that say through temperature and load, PUE can fluctuate as far up as 20%. And I think this is where some of countries outside of the US get a little bit bent about PUE, is anytime you use a metric like PUE, the way it's designed to be used, is very effective. I do see a lot of people that I work with, a lot of colos, where they'll say, hey, our PUE is 1.3, and that's what they advertise, and it becomes a marketing tool. It may have very well been PUE of 1.3 at that point, but I can guarantee you, if you go back 10 minutes, 15 minutes later, or at a time where it's a different load, higher or lower, you're going to see a fluctuation in the PUE. And the point that it can and will fluctuate is a very valid point.
Okay, great. Let's see, we got another one here. Do foam blocks, blanking panels, and floor grommets really make that much difference?
Yeah, I think I glossed over this, but one of my techniques when I go into a data center, and I studied this in Ohio State, I'll go to every opening that I can find in the floor, around pipes, empty U's in a rack. And this is what I found out. When I would go to ask for money, and not a lot, say, hey, I need to fill these holes. And I'm like, what? Does it really make that much difference? So I had the understanding that I had to be able to show and quantify that there was a difference. So I started measuring, doing square inches into square feet. And that first data center floor plan I showed you, this was amazing. People understand this. Same thing, do we really need to spend the money on that? Well, you have a 497 square foot hole in your floor. They understood that. So yes, those things are not expensive, and your return on those is very, very significant, and you cannot achieve significant efficiency and power usage effectiveness in your data center if you are leaking air. And those items, those are the low-hanging fruits and the place that you have to start.
Yeah, and Isaac, I'd like to just jump in here. This is Lars again. Appreciate that, Kevin. And I want to go back to your slide where you mentioned that every ton of cooling is capable of dissipating 3.5 or 3.52 kilowatts of heat. That's true if it's fully utilized. So that's, the mathematical conversion of tons to kilowatts. However, because of all these openings and inefficiencies and poor airflow management, it's quite common for only about half of that cooling capacity to be able to be utilized. The other half is stranded capacity that's wasted in the form of bypass airflow. So just comparing that total installed rated cooling capacity to the UPS output load gives people a real quick indication of how well they're utilizing that installed capacity.
Yeah, Lars, thank you. That's a great point. And it reminded me, I don't know who I heard say this in a presentation, but they equated that to driving through the deserts of Arizona in the middle of the afternoon with your AC on in your car, full blast, and cranking all of your windows down about 4 inches. And I understood how that wouldn't really help my air conditioning, and the point you made is very good.
Yeah.
All right, well, it looks like we're here towards the end of our webinar. So if we didn't get to your question, we will go ahead and answer those offline. Kevin, thank you so much for joining us. And I know we cut your presentation a little short, but feel free to make your final comments, and we'll share the presentation with everybody here in the next day as well.
Yeah, really, I so much appreciate the opportunity to be able to share and collaborate. And this is what I would ask. If anybody on here, if I'm not already connected with you on LinkedIn, please send me an invitation. I would love to connect. And here's the realization. For this to fully work, for these webinars to be fully effective, I need to learn from you as well. And LinkedIn is a great way for me to be able to talk and learn from everybody that was on this call.
Awesome. Well, thank you, Kevin. Again, we really appreciate you joining us here for Airflow Management Awareness Month. And I would like to thank you all for joining us here as well as attendees. I shared a link for you to watch all the other webinars on demand from earlier in the month. So feel free to go through those if you haven't watched them already. Again, thank you, Kevin. Thank you, Lars. And thank you all for attending. Bye-bye.